So welcome to the talk, Essential RL Theories for Algorithm Developers. And this talk is under the help from Ming, Chengju, and Chava. And thank you for my supervisor and my supervisor committee members. So I have a really cool topic like essential theory. And what message I want to say about it? Just only one thing. Let's now try to tune our hyperparameters forever. We can do more than tuning hyperparameters. We can learn something from our theories, and we can try to understand our algorithms, understand the tasks. We want to know what is the limitation of our algorithm. We want to know the hardness of the task. And we want to know for this specific task, this challenge, what are the necessary techniques we need to solve everything. So that's the plan today. First, we will look at some counterexamples, which is not solvable by offline RL algorithm, so that we can understand the challenges. Then we want to know what could be the sufficient conditions to solve offline tasks. Then let's check how well those conditions are satisfied, and consider what should we do when those conditions are not satisfied. So what theory people is doing is like, we are searching for minimum sufficient conditions to solve a task using a reasonable amount of data. By reasonable, we will define it rigorously later. Here, we just say it's not huge. Like if it's Atari game, we do not want the data to be multiple number of the state space, which will be 10 to the power 6, 7, something. We don't want a huge number. And what people do is usually we start from a very simple condition. What does simple condition mean? It means previously all offline, I'm showing just the sets of tasks. Previously, we have all tasks joined by the outer circle. And then we add in a simple condition. Then only some tasks satisfy this simple condition. So we are dealing with a smaller set of tasks. And by giving this simple condition smaller set, we hope, then the task is easier to solve. But what people realize is maybe under the simple condition, we can find some really bad counterexamples, which are still not solvable using a small amount of data. We just find counterexample, then realize, okay, this set is not solvable. Just the something in it is not solvable. So what people do is we add more conditions. By adding more conditions, we try to remove those counterexamples, and we're working on a smaller set of tasks. And we hope in this case, this smaller set is all tasks can be solvable. And what people do is, okay, on this smaller set, on this smaller set, let's search for an algorithm which can solve all tasks in this smaller set. When we find the algorithm, we will say, okay, under these two conditions, they are all solvable, and we will give it a correct set.
So by solvable, you mean solvable using a reasonable amount of data?
Yes. And then when we find some conditions which make those tasks solvable using a small amount of data, we will think maybe those conditions can be too strong. Can we weaken them a little bit so that we can dealing with a slightly larger set of tasks? Just our algorithm can be more general. And then theory people may just encounter a counterexample again and say, okay, when we try to weaken it, it's not working again. So what do people do? Let's try to give extra requirements on this weakened condition. And then say, oh, if we can find an algorithm which works again. And people just keep repeating this pipeline, searching for some minimum conditions that we can use to, so that we can find an algorithm to solve the task using a small amount of data. So that's basically the broad idea of everything. Now let's go into details. Let's go into some setting. We're dealing with RL, so we work on MDP. And here I will use finite horizon MDP notations. But most example in this in this talk, they can be applied to infinite horizon with discount factor as well. And we have state space, action space, transition probability, reward. We denote our horizon by capital H. We have policy. Action value is defined as the cumulative rewards. Usually for online RL, the agent will observe the environment, receive state, reward, and then decide which action to take. It can keep interacting with the environment. So after observing some states, the agent can decide where I want to explore, where can give me more information. But in offline RL, everything is limited to a pre-given data set. We have this MDP, we collect a data set from this MDP, and then learning is limited to it. And why do people want this limitation? Because sometimes online data collection, the interaction with the environment can be unsafe. For example, we are dealing with self-driving car, robotic surgery. We don't want to try our unqualified policies. And another reason is online data collection can be very costly. For example, nowadays we're dealing with large language model. If we just keep updating all the parameters, receive new data, it's very costly. So if we can do it offline, let's just use this cheap and safer way. So more rigorously speaking, we will have a data set. And there are usually two ways to collect data. The first one is called oracle generated. We will have a sampling distribution mu. State action pairs will be sampled IID from it. The next state and reward will just follow the dynamic of MDP. The data set is composed of transitions. If we use language model as example, it's like we will randomly sample incomplete sentence from a distribution. And then MDP will generate the next word. And those transitions will be our data set. The other way people try is to use policy-induced data. The data set only contains complete trajectories, and each trajectory is generated by only one policy. So if we go back to sentence generation, it's like starting from the first word, we will generate the next one, and we will keep generating until we finish the complete sentence. And in this case, policy-induced data, we have complete trajectories. So we have more information of how states they are related along different time steps. So people sometimes intuitively feel, oh, it can give us more information than oracle generated data, can be a stronger requirement. Yes.
Oracle can be adversarial or it is beneficial?
It doesn't matter if it's adversarial or beneficial because there is only one time generating. Just we generate before we know anything. Yeah.
What does it mean by oracle here? It could be user generated.
Yeah, it could be user generated. It could be like we already have like language model. We already have many sentences online. So we just use those online sources and we don't really know what is the
prior available data. That's oracle.
Yes, just all those data sets, no matter oracle generated or policy induced, they are all just the prior information before we do any learning. They are just like text given online. They are not collected for our preference. They are just collected that way. And our goal here is using all those pre-collect data sets. We want to find a near optimal policy with high probability. If we look at this, okay, I have a right cursor. Let me find it. Hey. So if we look at the equation, this pi hat will be the policy we learn, and we want the cumulative root. Oh, they will miss the important part. Next time they need to come in person. Yes, and they also miss the pizza. We want our learned policy, the cumulative reward of the learned policy should be very close to the optimal one. And that's our goal. Yes.
You have this condition on the data set. Why not the data set might be very problematic. So you're not trying to find the best policy given the data set you collect. Right?
Oh, well, yes, that's true. Just the usually data set limit our learning power. But our goal is just is the perfect naive goal. No matter what data set, our goal is to learn the optimal one given the MDP. Oh yes, just we are given the data set. No matter what data set is, our goal is to learn the optimal one. Yes. Here we will just want to our goal here is only ensure when we start from the initial state, we can gain the optimal reward. Yes. No, just in this talk, we will deal with the simplified goal. We will only want to learn the optimal value at the initial state. Yeah, this is our simplified goal. Thanks for this detailed question. And then let's go into theory. So theory people are always worried about bound. First thing they worry about is upper bound. And just the upper bound is usually specifically to an algorithm. We just want to find an algorithm satisfy we just want to find an algorithm and upper bound. Oh, okay, let's restart this. Upper bound, what is the bound about? It's about the number of data we are using. So it's about the number of the size of our data set. We want to bound that. And upper bound basically means at most this many sample. People do is we can find an algorithm so that, 1 second, this algorithm can solve any tasks satisfying our conditions using at most this number of samples. Yes. Oh, we will study what kind of assumptions on data set are needed here, will be needed. That's what we are going to look into. Yeah, and here we have a very fancy word called worst case upper bound. It basically means we want to solve all tasks satisfying the condition. That means even the worst case, worst task in our set, we want to solve that. That's where the worst case comes from. And another thing, we have upper bound. Also, of course, we have lower bound. It's also a bound on the number of samples. It means sample need should be greater or equal to than this number. What it means, lower bound, the thing is, it's always independent of algorithm. No matter which algorithm we use, if we want to solve this task, we need more than this amount of data. That means if we use less than this amount of data, we can always find a counterexample which is not solvable. And this is not solvable by any algorithm. And why do we care about lower bound? So one thing is people really want to show I can find an algorithm so that my algorithm only use this lower bound amount of data, and then I can solve the task. Then I can claim that my algorithm is the best, because if I use less than this amount, no one can solve the task, but my algorithm use exactly this amount. So we show that our algorithm is best, and that's what people call closing the bound. People prove a lower bound at the beginning, and then we try to find an algorithm which matches this lower bound. That's the fancy thing theory people is working on. And the second reason we want to look at worst case lower bound is we can look into those counterexamples and say why they cannot be solved. This helps us to understand the problems better. Yes. Yes, usually people just deal with big O notation. And here the big O notation just is explained in this. Okay, I didn't really explain big O notation, but everything is under big O. And our roadmap here is we want to build up conditions to see which we can find counterexample. If we stronger it, can we find algorithm? That's we want to build a roadmap like that for offline RL. And here we call huge amount of data if the lower bound depends on the size of the state space, like Atari, which is huge, or it is exponential in any of the following term, either the horizon or 1 over the value arrow, because when we want to work on a slightly larger task, longer horizon, we don't want the number requirement to increase exponentially, which means everything is it's going to be very hard to generalize to larger tasks. So we don't want exponential data, and we will just give them a cross sign, call them unsolvable. On the contrary, if the bound does not depend on the state space size or its polynomial in all of the following term, we will give it a correct sign. We call it solvable. So let's start building our roadmap. So first thing, we just start from the simplest condition we can think. How about policy-induced data? Can you make a guess? Do you think it's going to work? No. Yes. The reason is already pointed out because people keep asking what assumption we need on data set. And here we only have policy-induced data, which let's see if it's enough. So people try to look at a counter example where it has h+1 states, actually h states, and that state is the terminal state. And if for all states they share the same action space, by taking the A star action, they will just move along this row. By taking any other action, they will just go to the terminal state Z. There is no reward except this right transition at last. The reward is sampled from a normal distribution with mean either +1 or -1. And we know we have two MDPs, one with +1 reward, one with -1 reward. And then the agent starts to generate data on this MDP. And people say, let's try to generate data from a very tricky policy. This tricky policy will just assign A star with the minimum probability. If it's minimum because we totally have A actions, then the probability of sampling A star must be smaller than 1 over A. So people using a very trick policy which sample this A star with very low probability. Then if we want to reach to this right transition, the probability will be very tiny, will be smaller than 1 over A to the power of H. And in this case, if we want to have a data set following this policy and contain this right transition, the data set needs to be at least the big O A to the power of H to contain this right transition. And if we don't contain this right transition, the agent will never know the reward is +1 or -1. So we require exponential data to really figure out it's +1 or -1. And only we know if it's +1 or -1, we know at this state we should take A star to receive +1 reward, or we should take other actions to avoid a negative reward. So in this case, unless we use exponentially large data set to know this right transition, otherwise this task cannot be solved. We will never know we should take A star or other actions. So people just build an context. This is counterexample meaning, and this is how people prove lower bound. In this case, people just show a lower bound exponential in age and show this task is unsolvable. And we can see the hardness is basically because the reward is hidden after the horizon with very low probability. No, all we have is data. So what we want is, we want better data, we want better generation way, which can cover the reward more with higher probability. We need a stronger data coverage requirement. And what people trying here, the first thing people try to add is, how about with, okay, so let's leave this better data requirement for later on. Let's go into a new terminology before we come back to data. We also want, the second thing we want about the data, the bound is it should be independent of the state space size. To remove that, people usually use functional approximation because it's tabular. We all know we have to visit all the states. So people use functional approximation to remove the dependence. And one example is just linear function approximation. Phi is the feature vector, theta is the parameter, phi is given, is part of the MDP. And we will try to learn a theta to approximate all the action values. And now we have to change our requirement. We also want our lower bound not exponentially dependent on the feature dimension D, because we may want to use a very large neural network, a deeper neural network. We don't want the data requirement to increase too insanely if we want to use a deeper network. And now people say, before we go to data quality thing, let's try to add in some structure assumption. Otherwise, if this, we are evaluating Q value in actor critique, in Q learning, in value iteration. If we have no requirement on how well those Q values can be represented, we can just we can be learning nothing. And of course, it's not going to work. So first thing people say, let's say Q pi for action value for all policy can be actually represented. Here is say for all policy pi, there exists a theta, so that Q pi exactly equal to theta transpose phi. And also in theory, people sometimes deal with, it can be linearly represented with very tiny error. Then these two things are basically the same thing. The proof will be very similar. And let's think, if we have Q pi realizability and plus the previous policy induced data, can they work? And somehow we already know just that the issue is not solved. The reward, just even we have Q pi is realized, we can still have a terrible data as before. And reward is hidden, reward shows up with very tiny probability, then it cannot work. So of course, no. What we truly need here is, even we have Q pi realizability, we need a stronger data quality assumption. And what can this stronger data quality assumption be? So first thing people say, let's borrow something from supervised learning. In supervised learning, people usually use feature coverage assumption to make their data set qualify. And because we have a big assumption here, let's try to read it line by line first. It says, for all state action pairs, assume our feature map is bounded. This is just a very normal assumption in theory proof to make everything simple. And then for each step H and each data generating distribution, it will generate state action. This mu H is the oracle generated distribution. It should satisfy some minimum eigenvalue condition, which is this feature information matrix expected over this oracle generating distribution. This matrix should have eigenvalue equal to 1 over D. And then it says, note that really means it's a fact. This 1 over D is the largest possible minimum eigenvalue this matrix can have. So this note that part basically state this assumption is strong enough. It's already the largest value this minimum eigenvalue can be. That's why we have the note that part. And I know everyone is super confusing here, just we are reading so many math notations, but what's the meaning of them? So first, how about let's try to understand, given this matrix, what does the eigenvalue of this matrix mean? So we plot our data set. Here, let's assume the feature is of dimension 2, and we plot out their features. The direction with largest variance will give us the first eigenvector for that feature matrix. And the magnitude of this eigenvector will be the eigenvalue. And then we will go to the second direction with the second largest variance, which is perpendicular to the first eigenvector. This will give us the second eigenvector, magnitude, the second eigenvalue. So we will continue it until the last eigenvector, which is the direction give the smallest variance. And here we say the smallest eigenvector should be lower bounded, means the data should have enough variance on all directions. Then there shouldn't be a direction uncovered, which means if we write out the feature information, we have that feature information matrix, we have our given data set, and we compute phi t for each data point. We sum them up. That matrix should have full rank. Because we have the QPy realizability assumption, we need all dimension information from all the dimensions to really represent the action values. So this tells us our data is strong enough to represent each direction very well. And what people figure out is, no, this assumption for supervised learning does not work here for offline RL. Let's try to read theorem again. So it's suppose assumption 2 holds. We already read assumption 2, and fix an algorithm that takes input with a policy and a feature mapping. There exists MDP satisfying assumption 1, which is QPy realizability, such that for any policy, this algorithm will require d to the power h samples to output the value of pi up to a constant approximation error with probability at least 0.9. If I summarize it, it basically says, if I want to read the theorem, usually the key point is, what are the assumptions I need to satisfy? And then here, what is the bound? It says for any algorithm, it requires this number of samples. Then it tells me it's about lower bound. And then I get out the information of the lower bound. Then I make my conclusion. Basically, it tells me under these two assumptions, the lower bound is exponential in h. And then we try to, and we want to just really read into this result and try to understand why that's the case, because it's very enough for supervised learning. Just under these two assumptions, supervised learning regression can give us good accuracy even under any test distribution, under any distribution shift. And compared to online learning, for online learning, as long as we have our policy realizability, we can definitely find an algorithm which gave us a near optimal policy. But what happened here? So first thing we know, the hardness of RL is, we already see from the previous context example, reward can be hidden after a long horizon. And another thing, just from this paper, I skipped the context example. If you are interested in it, we can discuss it later. They told us the noise from stochasticity of rewards and transitions can be accumulated along horizons and can be amplified exponentially. So I observe some stochastic reward at horizon h. The error is very tiny, it's just epsilon. But if I go backward from the horizon at the initial state, the error will be epsilon epsilon one, okay, how to say that? Like 1 over epsilon to the power h something, like that. Just the error is increasing exponentially. And the reason for that is it implies maybe our QPy realizability assumption is not strong enough. Or on the other hand, we need better coverage of MDP, just supervised learning thing does not work. Yes?
What do you mean by the arrow there?
Error.
All the 3 bullet points, you have an arrow?
Oh, just it implies, just from this point, it implies what we need.
What we need.
Yes.
We need. Yes.
Oh, sorry.
Given this implies that this implies we need to have that.
Oh, yes. It implies we need to have it. Yes. And the third thing is different from supervised learning is that usually for supervised learning, the target is observed. But here we need to based on bootstrapping. The true target is never observed. And when we based on bootstrapping, this bootstrapping can give us a bias. Same as before, this bias can be accumulated and amplified along the horizon. So maybe in this case, we want to consider using multiple step of rewards, like go to Monte Carlo a little bit, but it causes us the bias variance trade-off. And the more serious issue of using multi-step rewards in offline RL is like there is a distribution shift. If those rewards are not collected under our desired policy or the optimal policy, if we just sum them up, it's not going to be our target anyway. So we need to do a distribution correction for offline RL. So multiple step reward can be a choice, but we can not really go to Monte Carlo. It's not going to work either. And the third thing, and compared to online learning, the thing is we already know the quality of data set is really matters. So we already try figure coverage, and let's try some stronger coverage assumption. And what people use is concentration bound. Okay, are we ready to read it? So first, it defines what is admissible distribution nu. It means there exists a policy and the step h, so that this nu is equal to the probability for state action to show up at step h under this policy pi. And then after defining the admissible distribution, it starts to go into this condition. This condition requires a constant c, so that for any admissible distribution nu, the ratio between the distribution nu and our data generation distribution mu is smaller than this constant for all state action pair. If I simplify it a little bit, it means just I try to remove this admissible distribution definition here. It just means for all policy, for all time step, for all state action pair, the ratio between the probability for the state action to show up and our generation distribution should be smaller than C, which means our generation distribution should larger than 1 over C times this probability. It means for any state action pair that can be reached by any policy, our distribution should have a large enough probability to cover it. Is this concentration bound actually realistic? So for Atari, basically all states is reachable by some policy. If we want to cover all state actions, maybe what we can try is only uniform distribution. But the thing is, uniform distribution will be equal to 1 over state space size times action space size. Then this constant C will depend on the state space. That's what we do not want. So it basically means for a complicated game, this concentration bound may never be satisfied. It just tells us this concentration bound is already an extremely strong condition, which makes everything which is already very hard to be satisfied. However, in this case, even with this concentration bound, the result is still negative. And what happened to it? It's because people realize, okay, we assume this concentration bound, our data set of distribution need to cover our policy very well, but it can also contain some terrible transitions. Those like we may have an MDP just from the initial state. Only a part of the MDP can be reached. And also we have the other part, which can never be reached by any policy from the initial state. Those part, this concentration bound has no limitation on. And people can put a really awful data from this part into the data set and cause us an issue. And if we want an example, it's like we only want our cleaning robot to clean the floor, so it can never climb up to the shelf. But actually, our human can put it on the shelf, so those states still exist. And people can put those unreachable states into the data set and mess up the learning of the robot. That's the thing. And now we have two conditions here. We try feature coverage and all policy coverage. A question people always interested is one condition stronger than the other? And here actually no, just each circle still represents a set of tasks which satisfy this condition. And it realized these two things just go to different directions. And people somehow think all policy coverage is stronger because it's suitable for RL more. It tells us we can cover all policy very well. And people think it's just somehow aligned with RL understanding more. So that's why people may like this all policy coverage slightly better than feature coverage assumption. And now we have too many negative results. Can people actually find a positive result, find an algorithm? And just this year, Valad from Chava's group, they proved that if we use policy-induced data and their QPy realizability and all policy coverage, there is actually an algorithm to solve offline learning. And this policy-induced data means all data need to be generated by a policy. So in this case, we cannot add any spurious data into our data set anymore. And these two results combined together really shows us, okay, these two conditions, they are enough. The only thing, just the damage here is the spurious data, and it can be removed by trajectory data. Okay, so finally have yeah. Sorry, yes. The data observing may not, could you, which slide are you asking? Yeah, we can discuss later. So now we finally have a positive result. And our goal is to see, let's try to weaken our conditions. We already think that all policy coverage can never be met. So what people switch to is single policy realizability and coverage. Like previously, we assume QPy for all policy can be linearly represented. People think, how do we know all policy? There are just too many policies. How can we test all of them is representable? People think maybe we should only think about Q star realizability. And also for all policy coverage, people think maybe we just cover the near optimal policy, which is only for some policy pi star, which is near optimal. Let's just say our generating distribution has a good probability of covering data reachable by this pi star policy only. And in this case, like people realize we need to use very advanced algorithms. Like when we only have one policy coverage, then just we have so many extrapolation during our learning. An issue always just bother us is overestimation of extrapolation. And people really need pessimism. For pessimism, it points to two things. One thing is we use pessimistic value estimation. The second thing is we regularize our policy so that the policy, the learned policy is not so far away from the data set. That's what people, that's like trust region, what people use for PPO stuff like that. But pessimism, and also for the pessimistic value estimation, it's like clipped double Q, which is a way to add pessimism to our Q estimation. And then what people gradually realize is like clip double Q, they give too much pessimism and it really hindered the exploration. And people say, oh, maybe we want to remove this pessimism, but we still have very partial coverage. And people try to do hybrid RL. They have a qualified offline data set in advance, and then they allow the agent to do some online exploration. Like the data set is of size N, then they ask the agent to collect another N interactions online. By combining these two, people prove that, yes, we can actually remove pessimism and have a good solvable result under Q-star realizability, near optimal policy coverage, plus some other conditions here. And the third thing people are doing is, we don't want spurious data. Then we can directly try to model density ratio, because density ratio will give all bad data 0 weighting. Yeah, and then question comes, can Q-star realizability actually be satisfied? Even we only want to model Q-star, is it possible? And here people figure out, like they show a figure on the left, they show, they plot out the dynamic. X-axis is state, current state, and the dynamic is deterministic. Y-axis shows which next state they are transitioned to. We can see the dynamic is very simple, almost linear lines, piecewise linear lines combined together. But the Q-star, the optimal Q value, is very hard, it's very complicated. Just on the right-hand side, we have state as axis as Q value for the y-axis. And also this paper shows that for some environment, we have really simple piecewise linear dynamics. But if we have a constant depth neural network, the Ys of the neural network need to be exponential in age. Just either we have the depth depend on the horizon age, or we have the Ys to be exponential in age. Otherwise, Q-star can never be represented by a neural network. So in this case, basically, Q-star cannot be realized. Then maybe we shouldn't try all those model-free algorithms. Maybe we should do model-based, or we directly use reinforced algorithm. We skip Q-value part. So that's everything. Yes, we finished early. Perfect. Do not tune our hyperparameter forever. Let's go. We have some new tricks now. We can test, is our action value representable? Now, if it's not, we should go to deeper neural network, or we should switch to another set of algorithms. Is our data set qualified? We should, now the larger the better. We should really remove bad data. And also we should ensure we have good samples from the near optimal, the policy we want to evaluate more. And the third thing we consider, do we really, if we need advanced techniques like pessimism, hybrid RL, or density ratio estimator. Yes, and that's it. Thanks for listening.